Alright guys, sorry to say that, but it's a heavy workload alert for this week. It's due next Monday, right? Task 1 and 2 due next Monday. I'm pretty sure most of you haven't started yet because the last one was due Tuesday or Monday last time. Heavy load, I mean, it's a bit challenging. I think you want to be challenged. You don't want to have a very easy class. You want to be challenged, and it's very reasonable since I'm gonna write down some of the code and to let you get started. Again, so the goal is using two different methods. Task 1 and Task 2, they are using different methods, and Task 1 and Task 2 are due Monday next week or this coming week, 5 days from now. Okay, and Task 3 is a little bit more challenging, so it's due Monday, November the 3rd. Okay, the 3rd. So cover how to code up Task 1 and Task 2 today, mostly, and talk about Task 3, and probably we need to spend some time on Friday as well to go through all the key points in Task 3, and then we'll talk about PCB design, okay, to make you guys ready for job interviews, and so you can also start working on the cross project. And so what are the differences between Task 1 and Task 2? So Task 1 and Task 2 are doing the same thing. It's just sending one letter. So one letter, it's basically just the ASCII code. It's 1 byte. Okay? So you press S, you send 1 byte. And it's being wrapped by a start bit and stop bit. So it's only 10 bits being sent. Okay? So you press S, it's being sent. It goes to the air out of control, right? And the receiver will receive it, it will capture it. So my question for you guys is how these UR modules know the byte is coming, because your finger cannot beat the speed of the transmission, right? You press S, something's out, it's out of control, okay? And then it takes a second at least for you to move your finger to the keyboard to the R key, and you press R to receive it. How do you manage that? So the thing is, we press S, it's out in the air, and your detector will receive it. It's in the speed of light. Your fingers can never, beat that speed, right? And then you take another second, you move your finger to the key of R, you do a Shift R, it receives it and display it to the monitor. So that's what we are going to see in Task 1 and Task 2, but using different methods. But let's think about Task 1 first, right? Task 1, using the method without SR, okay? How that works. So do you think that the moment you press R, it starts receiving? Or you press R, it's just reading it from something to the monitor, which means the data is already ready in the microcontroller. Which is most likely?
There's a buffer.
There's a buffer, right? There's a buffer. So how do the buffer know the data is coming?
It sees the start bit.
The start bit. Because when the pulse is going into the air, being received by the decoder will see that pulse, the first pulse, series of pulses, which will do what? Will output a what?
0.
Output a 0, it pulls it down. See? Pulses will pull it down. Okay? So which means before it's being put down, it was a 1, right? Why it was a 1? Why there was a 1 over there? You have to turn it off, right? You have to turn it off. Where there was nothing to be sent, so you have to turn it off. So in that case, whenever the first series of pulses being received, it pulls it down. It's being recognized as what? As a start bit. Okay, so the UART what? UART 0, 1, 2, 3? Which one? Remember? Uh-huh. UART 0 is for the USB. So UART what?
One.
UART 1. UART 1 is the one you want to customize, right? It's a customized speed or baud rate. So that one detects that put down, which is the start bit, and then start receiving bit by bit, or the whole byte, one by one, and end it with what? A stop bit, which is put up, right? So that 10 bits was already sent by the S key. So you press S, it will do the 10 bits for you, and the UART1 module will be able to start from the start bit and then receive all the following bit and then detect the stop bit and stop. So after press S, the buffer in the UART1's module will be able to receive and store that byte into it. It's already there. Okay? It's already there. So then you press S, you read it out. You have a little index, you just read it out. Okay? I should not, because it's just one byte, right? Just one byte. You just directly read it. So which function to be used for the reading? For reading it out, what's the function to be used?
Print line.
Oh no, read, not send. Let me see, where's the first one? First one. Yeah, see, the R case is given, so don't have to worry about that one. So it's given. How to read it? Serial 1 dot read, parentheses, right? So this will read it. So this function is going to return that, receive the data in the buffer, or in the little register. It's a receiving register. And for task 3, since we are customizing everything, so I have to directly read from that register. But now this function will return the value from that register to whatever on the left-hand side of the equation. So which is received, this character here. It's just one byte. It's very simple. It's right there. This one, right? This one, you press S. It's trying to see if something is available in the buffer. Okay, if something's available. If something's available, the first function here will return a 1. So this condition will be satisfied, and then it gets into it. So when you press S, something will be received by the UART1's receiving module. Okay, and this one will become a 1. Okay, will become true. Become true. And then you do a if statement. So we press R, it checks that condition first. If something is already received, we'll check that condition and then read it. Okay, then you do the following prints, whatever format you want to format it. That's your job. It's already given. You don't have to modify it. Is that clear for the whole process for task 1? Okay, so how do you do S? That's a question here. So for task 1, keep in mind if you have ISR, or if you don't use ISR, like task 1 is not using ISR, then your turn on and turn off the PWM will be a little bit different from the one with ISR. So turning off is the same. You probably want to write it down somewhere because you'll see this issue a lot. I already spent a lot of time to troubleshoot it. It's not written on any of the textbooks. It's just from practice, you know. If there's no ISR, you are manually turning on and turning off your PWM. This is how you turn it on. 3 lines. You have to follow it every time. 3 lines. Turn it on, turn it off. Have to follow. For every single bit, it's different, right? If it's a 1, you need to turn it off. If it's a 0, you need to turn it on. So turn it on, have to follow 3 lines. Turn it off, just 1 line. So for both ISR or non-ISR coding, turning off the PWM will be the same. Put it down somewhere, okay? Turn it off is always the 1 line, okay? 1 line. But turning it on will be different. If you have ISR, we want to turn it on in the ISR, you only need to turn on this bit. Okay, how? It's basically TCCR5A bar or equal this thing. You only need to turn on this thing. Turn it off, you just need to turn it off. Turn off this bit. Or turn on this bit. With the SR, with an SR. But now task 1 is not using SR, so I have to use the whole thing, the 3 lines, to turn it on. Okay, so LED on definitely will be a number. What that number is? What that number is? OCR5B, what is that?
Is it the time, the count that needs to be on?
Duty value, right? The duty value. Remember? Here. OCR something. OCR NX, right? OCR NX defines the duty value or duty cycle. You are doing 10%, and you calculate it ICR5, and you do a 10%. Just do a 10% times this value to find out LED on's value, right? So so give this value to it, the PWM is going to output that certain duty cycle for you. Okay, so that's the routine for the timer. Remember how long it takes? How long it takes for each cycle here for task 1? How long it takes here or here for half period, or maybe just 1 bit? How long it takes? What's the frequency of the PWM? All different kinds of questions, confusing a lot. It's very confusing, right? So what's the frequency of the PWM? 38 kilohertz is over here, right? It's this guy, 38 kilohertz. And the bit rate is for what? For UR1. Okay? So this thing is for UR1's baud rate. What is that rate for task 1? What's that rate here for task 1? Remember? 1200 bits per second. Okay? So for the timer, you turn on PWM or turn off PWM, you should follow the timer's definition or the baud rate you're trying to use, right? So the baud rate will be 1200 bits per second, so the time for this period will be 1 over 1200 second. Right? So the timer, if you are using timer 3, am I losing anybody? Am I losing everybody? Let me ask you a question, okay? Let me ask you that later. Make your life easier, that's right. So, timer 3, for timer 3, how do you calculate it? You need to know prescaler. What's the prescaler? It's 1, right? It's 1. And let me see if I gave you that number here. No, I didn't. Okay. So every time, it's given. It's given actually. This one, right? So the equation, the code is given. So you have to use the 16-bit, this guy, minus the desired time delay here, the counts. Okay, that counts will make a 1 over 1200 second. 1 over 1200 second, that amount of time for this time delay. So basically you turn on, set up timer, turn off, set up timer. So that's how you do it. And based on its start bit, it's a start bit or the data byte or the stop bit, right? You turn on or turn off the PWM accordingly. So start bit will turn on the PWM, okay? So stop bit will turn off the PWM. And for the bytes, every single bit in the data byte, you have to use the mask to detect it. So the mask has LSB to be 1. And do a bitwise AND like this. If the bitwise AND detects a 1 at the LSB of the data, of the light or the ladder is ASCII code is byte, right? So it's a byte. Okay, the ladder could be, for example, let's do send a 5 first, or send an 8, doesn't matter. So in that case, in your code, you have to declare the ladder to be a character first. Okay. For example, I did a 5 in the demo. You can put an A, put a whatever, and because that character has ASCII code, so whenever you are doing a bitwise AND, it's doing an AND logic with the ASCII code with the byte, and it's gonna so the mask do the AND logic first, and it's gonna detect the LSB of the data first, and then if it's a 1, question for you guys. So if you detect that the LSB of the ASCII code of that letter is a 1, do you want to turn on or turn off your PWM? If it's a 1, turn it off, right? Turn it off. If it detects 0, you want to turn it on. Okay, that's how you want to code it up over here. So if letter and a mask, I didn't see anything, which means it's a 1, right? If it's true, what you want to do here? You want to turn off the emitter. How to turn it off? Just that line, right? Just this line. Just put this line over here. It's already given. Just put it here. Else, which means it's a 0, which means it detects a 0 for that LSB of the data. Then you turn it on. So how to turn it on? Just follow that 3 lines over here, okay? And then shift your mask to the left by 1 bit. So you're able to detect the bit 1. And then just keep doing that. So the bit 0, bit 1, bit 2 until bit 7. So every single bit will be detected, will be like monitor, whatever. So will be ended with that mask. And there will be a certain PWM being sent. All right. So my question, another question here is, would you like to put the LED on or off? No. Would you like to put a timer because you are putting it on or off, right, for these 2 parts? And where should you place your timer's time delay? I mean, turn on the timer while turn off, just a timer thing. Where should you place the timer? After everything here, after the while loop, or after the if statement, or after every single if and else? So my question is, you want to put a timer thing here behind this guy and behind this guy for both, or you just put a timer after this if statement, after this thing, or you want to put the timer outside of the while loop? Which one? Where the timer thing is should be placed at? So if you put the timer, so turn it on, right? So turn it on, or like it says here, you turn it off, right? Turn it off, and now I turn on the timer because I placed it at 0, right? It makes sense. I turn the timer to delay for 1/1200, okay? Which is fine. If it falls into this category, I need to turn it on, which makes sense as well because I turn it on. I turn on the timer to time that period, which is 1/1200. Or I can put it outside of the if statement, which means doesn't matter which condition getting satisfied, I just turn on the timer and time it. Or if I place it outside of the while loop, which definitely is wrong because, you know, it should be within because it's doing every single bit. Every bit deserves a timer, right? Every bit you need a timer. So that is wrong. But what about the first 2 cases? Which one should be better? Within the if and else, or outside of if? Outside of if else. Inside if and else, or outside if else? It's a little bit redundant, right? Because if it's inside if else, it's a lot of times not being used. If it's outside of if and else, because only one condition will be satisfied, and eventually it doesn't matter which one is satisfied, you just do the same amount of time delay. Make sense? So it doesn't have to be within the if and else conditions. It just has to be, there's just one timer block outside of if and else. Okay? All right. So Keep doing that, and that will send the data byte. And make sure that after you send the data byte, you want to send a stop bit as well. Don't miss that one. And also, before you do this block, you also want to send a start bit as well. So start bit, which is turn on the PWM, right? And then set up a timer. So you can see the routine here is you give a count to the timer, you turn on the timer, you wait here while it's counting, and after the timer's up, it's getting out of the while loop, and then you stop the timer right away. And then you clear the overflow flag of the timer. That's the routine you have to follow. Okay, every time you turn on the timer, you have to turn it on. You have to follow these 5 steps every time. That's for task 1. Okay. So one little tip here for you guys is you have to use. So for task 1, you are not using ISR, so you don't have to do this, right? You're not enabling the interrupt, so don't include that in your setup. However, keep in mind, this is required in your setup function. It's not written in any of the textbooks. It just wouldn't work properly if you don't have this in the setup function. You have to clear your overflow flag of the timer 3 in your setup function. You just have to do it. Okay? Even though you think, hey, I'm clearing that bit by doing this in every timer setup, in every timer's block. However, if you want to start the timer the first time properly, you have to do this in your setup function, just to let you guys know. Okay? And the demo font size is pretty small, you couldn't really see it, but like what I just described, you press the S, you send it, and you press R, you receive it, and turn it to the serial monitor. That's what you are expecting for task 1. For task 2, okay, it will be simplified a lot, and the programming process will be a lot nicer, and it's just a lot easier. I mean, whenever I just do it in the one loop, because Arduino has a loop function, right? So setup and loop function. If you are handling everything one loop function, you turn off the timer. There must be something is messing up the backend on the backend, and eventually it's not working properly. It's just so painful to program everything in just one loop function. However, if you integrate your ISR in your loop function, it just interrupts and get all the jobs done in the interrupt. It's just a lot nicer. It's a lot easier. I mean, it's probably took me 3 times longer time to do the non-ISR one compared to ISR one. It takes so much time to debug it. Even so I found out this guy, this thing, by accident. I don't know. There's no answer from Google. I just directly added. I was thinking, hey, do I need to clear this overflow bit in setup? Is that a reason for that? The error data that I kept receiving, and I tried it worked. I don't even know why. It just does the hardware design. They just don't like it. Okay. So ISR will directly, every time it enters ISR, it's going to clear this bit by itself. So it's pretty nice. And for the ISR version, what we are doing in the ISR is we send it using the ISR. So the receiving block is still the same. Receiving, you press R, it receive it. It's not changing. It's in the loop function in the switch cases. And for the send function, we place so we don't have the lengthy case as anymore for this one. Like the task 1, you have this, right? Have this. And also turn on, turn off, start bit, stop it, you do this. For task 2, if you want to get a full credit, you shouldn't send anything in as. Okay? So you also do as. However, you press as. Keep in mind, it's recorded, you can always come back, but the requirement is you press as, it turn on the flag. Okay? And then the ISR will keeps getting to the ISR all the time, no matter you press as or not. However, if you don't press as, the flag's not on. Whenever it gets to the ISR, it will stay at idle. Okay, so you're expecting what? You're expecting something like this. Case as, right? Something like a flag. You can rename it. The flag becomes true, okay? So in your ISR, you have idle state. Okay? If flag is true, okay? If you don't press S, it will interrupt. It will interrupt. However, it will stay at the idle state because this is not getting satisfied. It will detect the idle state. You have to do an initial state over here assignment. Just look at the previous examples, right? So it's gonna, the initial state should be, it's static, right? Static. And state equals what? State should be idle, right? At the very beginning. And every time it changes. So if it detects this one, if it's not detecting it, it goes to idle, it's not changing. Next time it will come back to idle and it's not do nothing and then break. It will break over here. Okay? So if you press S, this becomes true. And next time it interrupts, it will detect this flag and then jump to the next state. Okay? And the next state, you do your start bit, you do your byte, you do your stop bit. So the data byte is the mask method we just covered. It's the same code. So the only difference is what? Is there any difference on turning off the PWM? No. Is there any difference on turning on the PWM? Yes. I just talked about that, okay? Remember the method for ISR and non-ISR? For turning off, they're the same. They're the same. The one line. This. Turning off, they are both the same. Turning on, non-SR, you got 3 lines. Turning on, with the SR, turn it on, you only need this, right? So it's going to be TCCR5A 1 like this. Alright, so when you are sending the 10 bits, you follow the certain order, right? Start bit, data, byte, stop bit, then you're done. Doesn't matter if it's SR or non-SR. For non-SR, you do everything in the S case. For SR, you turn on the flag in the S case, and then everything when it interrupts, it detects that and then go to the data transmission block. And in there, it's more concise because you only need this one line to turn it on. But also, definitely you need to assign this guy there as well. Do you? You can try it. Probably not. So you can do this because it's just one assignment. You can declare this one in the setup or on the very top, right? So just once, you can do it on the very top just once, and then this will be remembered. Will be memorized by the. It will be stored in the register, and then every time you just need to turn it on and off, right? If you turn it off, it's getting disconnected. If you turn it on, it will directly apply this number to it. It will give you a 10% duty cycle. Okay. Remember why we need a 10% duty cycle for PWM? What are the reasons for that? It could be an interview question, right? You're talking about whoever interviewing you that they will ask, right? What kind of projects you have worked on in your undergraduate? You can tell them we customize the IR transmission and reception, and we coded up the baud rate to receive it, and they'll ask you, hey, what's the duty cycle of your PWM? You're telling them 10%. Why 10%? I don't know. The instructor just told us to use 10%. Why not just 1? Just DC voltage, DC 1. Why? Because IR is, as LED is running a lot of current through it, right? It's at the half amps level. It's a lot of current. The reason that we need a high current is because it's sending out the data. We want a longer transmission, so we need a larger power, right? Larger power for longer distance of transmission. So in that case, it requires high current. If it's a high current, and the device physically cannot handle the high current for the whole time, so we're going to reduce the power by using PWM, right? Instead of DC. DC is going to burn it. It's going to burn it. It's going to damage it. So reduce the power by doing pulses instead of constant current. So that's one of the reasons, right? And that's a routine for programming the non-SR and ISR version of task 1 and 2. Okay, any questions on that? Can we move on to task 3? Any questions on task 1 and 2 due Monday? Is that doable?
So earlier you mentioned like 1/1200. Do we put that inside the baud rate selected of the time count 3?
Yes, that's a count. That's a count. So that count you need to calculate, right? So if that's a very good question. So you can have a list of different baud rates in the list. So you can use the index to choose which one to choose. However, since we know what we are going to use, we just directly put a constant in there. So for this one, you could just throw a number to it. I don't really care. So you calculate that 1/1200, right? And you use a timer 3's frequency with a per scalar 1-to-1, which is still 16 megahertz, right? And you use that one times 1/1200 to find out the counts. And that's the number to be plugged into here. Exactly that number. Remember, right? So that's how you calculate it, right? So it's 60 mega times per second, right? So you want to times a time to cancel out the second to give it the counts. Any questions about task 1 and 2? Can we extend it to Wednesday? Nope. What's that?
For task 2 or
Uh-huh.
4, is that kind of like the state diagram you went through earlier?
Oh, that, because it's very simple, so I don't think we do need it, since it's only 1 byte. Whenever the flag is on, you jump out from the idle state, then you directly do your transmission. So you can get all the data done in the transmission state. And I don't think you need to stop it, because it doesn't really matter, because you send it, you're done. There's nothing else to be worried about. No, that's it. You just need 2 states. Idle, you jump out of idle, you do your data transmission. So another, in your data transmission, you want to do a check. So it's better to probably let you guys know that will save you another 5 hours. So in your data transmission state, think about it, okay? Think about it. So when the mask is shifting to the left, until which point you want to send a stop bit? Because you are keep shifting the mask, right? And you know that if this is the data or you're done with the data transmission, you want to send a stop bit. How could you know that? Do you understand my question first? Where should you place your stop bit transmission? Where will be the better place to do it? Let me draw it for you. Okay, it constantly going into SR. I have idle state. I have a data transmit. Let's say TX, okay? 2 states. Here's the if statement. If the flag is true, you do your thing, right? You move to the next state. What else you can do there? Keep in mind, whenever it gets into here, it will come back to this state every time it interrupts for 8 times. Okay? It will keep coming back here for 8 times, the 8 bits. Is that true? Let me see. No, it comes once. It comes here only once, and it will finish all the transmission first, all the bytes first, and then the next time it will come back here to see if you are done with it or not. So if you are doing your mask, that routine code here, like this, you are placing this part in there, right? If you place this part in here, so that will be your data byte, because it's 8 bits, right? So the mask is shifting by 8 times. You are sending out 8 bits. So where's the start bit? Should you put it here as well, or put it here? Where will be the best? So let's see, if we put it here, what's going to happen? So the first time it enters the data transmission, it do the start bit, okay? And then if it finishes the start bit first and then get into the data bit transmission, it will be a little bit hard to control because you don't. The next time it enters here, if you are not finishing your data transmission yet, you don't want to resend your start bit. So when you are programming the state machine, you will find out. That's why we need the different states, because we just want to do it once. Right? So it's better to put your start bit over here, because you know it's getting started, right? Why not just put it here? So just put it down and detects it and directly get into the next time it interrupts, get into this state, and we'll do the mask thing, right? So for the 8 bits. Okay? However, you need to check one thing. If I'll directly write it down for you. Okay? If mask is 0, which means all the bits, that little 1 here is a mask, the little 1 here is already shifted out. So the mask becomes 0, right? Which means all the bits of the data has been sent. You want to do something, right? Else will be this part. Start bit is done over here because it detects the flag and then moves to here, so it starts checking if the mask is 0 or not. If mask is 0, which means the transmission is done, what you want to do? Stop bit. So stop bit will do what? Stop bit is a 1, right? Is a 1. So we're gonna turn off. Okay? Do you need a timer? Do you need a timer 3 to time it every time? Do you need that timer block? Turn on, while, turn off. Do you need that? If you do, where? If not, why? What is this in? Where? Okay, so how ISR, so when it interrupts, when? How long it takes to interrupt? Or what kind of vector I'm using here to interrupt it? Huh? Which one overflow? Which one? So what? So the question is why I'm using ISR? Why? Reset, so it interrupts every time, right? So it gets into here every time. So it gets into here every time. If I'm sending a data or doesn't matter, start bit, or data bit, I need a certain period to change to the next bit, right? Doesn't matter which bit I'm sending. And what is that rate? The baud rate. So it's basically I'm sending every bit every time. I define the bit I want to send, and then next time I come back, I check it, I decide which bit will be the next, right? And that duration will be the ISR's duration, and I'm still using timer 3 to interrupt it. So you want to set up your timer 3 to interrupt at 1/1200. So it gets into here, decide a bit to be sent, and we'll do it. It doesn't matter if PWM or ground, right? and the next time it comes back, we'll change the bit for the next one. So in that case, every time after all the states, there's a very critical line that I want to include in there. And what is that?
After you finish the mask? Like after
After the stop bit.
Go back to idle.
Go back to idle. Do we need to go back to idle? You should, right? Mm-hmm. And what else?
You just
Yeah, definitely you should go back to idle. What else? So where to go back to idle, just in case. Another question for you guys. That's from Luke. Don't blame me. I'm just kidding. Where is that back to idle state should be plugged in?
set the state. Yeah,
But where?
never mind.
Because you set after the stop bit, right? Should be here. So whenever mask 0, you place the stop bit and then you change the state to idle. Right? So it gives it the time to make the stop bit 1/1200 second, because the next time it comes back, interrupts, it will detect the idle and stay here, right? But not this time. So we'll still give you that 1/1200. However, there's another thing which is critical as well. What's that? What is that? You do need it. So put a state. Yeah. What else is required? The timer, right? The timer. So the timer is set up, is turned on in the setup function. Oh, another question. So when you press S, would you like to turn on the timer when you press S, or want to keep the timer on all the time? Or does that matter? You just put the timer in the setup, which is fine because you are using flag to control it. It's okay, right? The timer is on, it interrupts, it's fine. Nobody cares. It's probably wasting a little bit of power, but that's negligible. It's nothing, okay? So it interrupts. If it's not detecting the flag, it's okay. If it detects the flag, it do the job, right? And so the timer is turned on in the setup function. So whenever it interrupts, it gets into the interrupt and execute the code over there, and then the overflow flag will be cleared by the ISR itself, which is running behind the scene. You couldn't tell, you couldn't see, but like I told you guys, one of the benefits of using ISR is that it will clear that overflow TOV3 flag by itself, so you don't have to do that one. Okay, great. But what else? The timer counts is also cleared, and there's no mechanism that set up the counter for your desired timing again. Okay, so once it finishes all the code in the ISR, what you want to do? So keep in mind, whenever it enters ISR, it already overflowed, right? Otherwise, it won't enter ISR. Overflow means what? It counts to the maximum, where it counts to the setup, the desired count, and reset to 0. So what's in TCNT3? 0. Would you like a 0 after that?
No, you need to reset it back to
Yeah. To what?
to whatever.
Whatever 1/1200. So it's going to be TCNT3 and 0x100 4 zeros minus 1/1200 times 16 million, 16 mega. Does that make sense? Where should you place that? Where should you plug that line at? Where? At the very end, whenever everything is done, outside of every single curly bracket, but within that ISR's curly bracket. Okay? At the highest level, just after every single thing, right before the end curly bracket of the ISR, you place that single line over there. All right, any questions on this? Can we make it Monday?
Shouldn't you do it when you shift the mask, though?
Hmm?
Why wouldn't you do it right after you shift the mask?
Shift the mask, because shift the mask is not ready yet. So stop bit will be ready, actually. So this will be the end of that of the stop bit. I think you could put it here. Wait, no, because
That's only after every fight.
no, because the counter needs to finish. So once 0, it enters here. If you reset the counter, I think, is it going to wait? So when it reaches, it runs it, clears the counter. I don't know what's gonna happen actually, but I think the better practice is just to place it at the end. You could try it here, see if that works. Something funky probably is gonna happen, but I don't know. So the another key point here is the code being executed in the ISR are actually pretty fast compared to the ISR's interrupt duration. So we are doing like 1 over 1200, and all the code being placed, like whatever here, being placed in the ISR, probably will be done in several microseconds. It's running pretty fast. So compared to the ISR duration, it's pretty much negligible. I think if you have ISRs like this, it probably only takes this much of time to finish all the ISR's code, right? Okay. So we don't have time to go through anything on the in-class number 9, so we'll cover that, and also the task 3 on Friday. And the key difference between task 3 and task 1 and 2 is task 1 and 2, we are just pressing once, we send 1 letter or 1 ASCII byte, and we receive 1 byte. But for task 3, I can show you really quick. It's just a little bit fancier, but not too much.
So 205 task 3. And for this task, the serial monitor of the Arduino software doesn't work anymore, so you have to use PuTTY here. And I saved the session over here, and I want to open it up, just double click it. So you have to press M, lowercase m, first to enter a string.
So press M to start typing your message. So you are sending a message instead of just 1 letter. So press M, you start typing a message in there.
So let's type hello world first and press enter.
So
and
press enter is being saved in the transmission buffer or transmit buffer. Okay.
then uppercase S.
So you press S, it's being sent. So it keeps sending every single letter with the stop and stop bit, start and stop bit. So every single letter has 10 bits. It's sending 10 by 10 every time. And then your receiving buffer will receive it.
So you can see hello world is already transmitted, and then press uppercase R to receive it.
So even though it looks really simple, it's just showing hello world, but actually it's already goes through the air. So it's already goes through the air and then received by the decoder and then being received by the buffer. So if I'm sending hello world, it's actually sending hello world and then being received and being printed into the monitor. And because the Arduino serial monitor is not able to do several certain things in order to let you type, so it's actually you have to press the send to show whatever you are typing. So you have to use a different serial software called PuTTY, P-U-T-T-Y. It's a very popular serial monitor, and it's available. It's free online, and I'll let you guys download it by yourself. I'm not sure you can do it for the desktop though, but if you have a laptop, you can do it. If you don't have a laptop, just let me know. We can figure something out. So because there will be a lot of errors that may happen in the air, so we used a checksum, which is an error check. You type whatever you are typing over here before you send it. You add all the characters ASCII code to a variable called checksum, and that's why you are seeing 125 125 over there because that's, wait, checksum is what? 255? No. Oh, 125. So 125 is the value of all the ones you typed, and you send it. What's being received by your microcontroller will add all the received letter together and calculate all the added ASCII code, the bytes level number as well. So you can compare, see if there's any error being transmitted, error message being transmitted. So I'll give you a lot of examples and write down a lot of example code during the lecture on Friday. But this is still third of November, so we still have a lot of time to work on it. Okay? All right, that's it.